Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, let's continue our computational fluid dynamics CFD videos. In this video, we're going to talk about carrying out simulations on a centrifugal fan, but in Fluent. Hopefully, the previous videos we talked about how to use CFX for computational fluid dynamics for here. Okay, for many Turbomachinery devices. Here we'll start an axial turbine using Ansys blade modeler and centrifugal pump and CFD radial turbine, and here the setup of CFX and the axial compressor. Okay, and a radial turbine here, static structural simulation. Okay, so in this video we're going to talk about using Fluent. Fluent is somehow different from CFX. CFX you can use it for modeling the using here BladeGen. So BladeGen is how to generate the flow path around the blades from scratch. Okay, and also you can use Vista, all kind of Vista here. You can use it for the simulations from scratch. But if you have your own model, also you can use the geometry for blade modeler, and then you can carry out the mesh using turbo grid, here turbo grid, and then you can use CFX for the solvers in CFX, K epsilon and SST model according to your license. So there are no many options like Fluent. Fluent is more powerful, I think, than this, but in CFX you can also use largely AD simulation according to your license. So in this video you can see the different ways in using these softwares. So basically, centrifugal fan is a mechanical device for moving air or other gases. So the terms blower or squirrel cage fan, because it looks like a hamster wheel, are frequently used as synonymous. Okay, synonymous. Okay, a typical backward curved centrifugal fan where the blades curve away from the direction they rotate. You can see here the different shapes of the centrifugal fan, and here the forward curve and backward curve. So the forward curved, okay, here are the rotation and here are the orientation of the blades, but the backward curved is like this, and here are the radial. So every well back we have here the sorry, you can check out all the things of the theory here, and different designs. Also you can check out the videos or the lectures. Here fans, blowers and compressors from India, and there are many videos for this, and also compressors and many things. Okay, also for the computational fluid dynamics you should use these books or references, are very useful to understand the basics of the CFD. Okay, the mass conservation, finite difference method and finite volume methods. solution of linear equation systems, unsteady problems, solving Navier-Stokes equations. Okay, the complex geometries like the turbomachinery, the choice of grid. If you do not have to use turbo grid, you can use or generate the unstructured mesh because it's more suitable for the complex geometry like this. Okay, the wings of the turbine, and here is to the basics of the equations and the generating the mesh, and I showed the unstructured mesh. Okay, and the turbulent flows introduction and many basics and K and epsilon and these things. Okay, also, and here are the contents. Let's check it out. So introduction to numerical methods, what's CFD, and here are the numerical grid. And here are the simplified mathematical models, incompressible flow. Okay, and the approaches and the CFD, self and discretization. And here are the 2D block structured grid, and also you'll find here some of 2D unstructured grid. Please check out the difference between the structured and the unstructured. Also, you can attend this course okay from this great professor, Foundations of Computational Fluid Dynamics. It will help you very much to understand the basics of generating the mesh and using the equations of the CFD. Okay, so in this video basically we're gonna talk about how to carry out 3D numerical simulation for a centrifugal fan. Also, I'm gonna show you how to calculate pressure fluctuations in the inside the fan, like this great paper. Those are Spanish researchers who are one of the greatest researchers using Fluent in this turbomachinery research. Here there are 2D mesh. Notice that there is unstructured mesh, but you have to make an inflation around it to capture the boundary layer or the more accurate model. And here are the 3D. Okay, and here are the pressure fluctuations and fast Fourier transform. We're gonna talk about how to calculate the fast Fourier transform like this, but this is in centrifugal pumps. Okay, the vibration. So analysis of vibration measurement data. So there are many different methods available for analyzing vibration data. The most basic method involves displaying the vibration data in frequency domain, also called the vibration spectrum. The frequency of the vibration is the number of vibration cycles per time unit. The vibration spectrum is fundamental to vibration monitoring because it yields the information that is effectively hidden in the vibration waveform. Vibration spectra can be represented in various different ways, of which the fast Fourier transform, FFT, Fourier transform, and the power spectral density are the most popular. The concept of vibration spectrum can be simply explained by means of an example. So consider the time waveform in figure 6 which has a frequency of 10 hertz, we can count 10 cycles, 10 complete cycles during 1 second, and amplitude of 5 millimeters, like this: 1, 2, 3, up to 10 here. And here, this is the time domain, and here is the FFT time waveform. So notice that here is the amplitude from 0 to 5 millimeters, and here is the amplitude also 5 millimeters, but 10 per second. Okay, so here are the hertz. So the time waveform a plot of time versus the amplitude, and is referred as to the time domain. Okay, and so on. You can check this. But what if you have here a waveform like this? So if you add this to this, you'll find this is the S1 plus S2. So the FFT, here the beauty of the FFT analysis, you can get this amplitude, large amplitude and a small amplitude, but at another frequency. Okay, so you can check out your system if there is a small amplitudes and what is the frequency of them, and the large amplitude, what is the peak FFT and at which. And mostly the first blade passing frequency is very important for this. Okay, so the first blade passing frequency is the multiplication of the rotating speed PF. So blade passing frequency, well, the multiplication, so noise level intensity varies with the number of blades and rotation speed of the wheel, and can be expressed as like this. Okay, so according to your design, you can get your blade passing frequency. There is a first blade passing frequency, second blade passing frequency, and third, according to the RPM. Okay, so we have here, if a fan 10 blades rotates with 2400 RPM, the blade pass frequency can be calculated like the multiplication of this RPM, but you have to divide it to get the revolution per second. Then you can get 400 hertz. Okay, so now let's check out our design. Here is the impeller or the blades. You have here this blade, and then you can carry out a circular pattern, but this is the blade itself that will be manufactured, but I need to carry out the flow around it, or the fluid path, like what we did in CFX. So here is just quite different. Okay, let's start. Okay, let's carry out a new project. So it's Loft Fluent, and I'm gonna show you now how to carry out the fluid path around these blades. Also, the benefit from using CFX, the time consumption. Okay, CFX only you can carry out the simulation or solving. Okay, here we go. Import external geometry. Where the final impeller? Yes. Add frozen. Yes. Here is our impeller. Please transform it. Let's try random 1 meter. Yes, here we go. No problem. Okay, so here are units in millimeters. Now please minus 74 for x 10977 and 74 through 16. In 977. Yes, concentric. Okay, very good. And the distance from here to here. But before doing this, just import the volute. Add material, must be add material, and here we go. Okay, now we have to get the volute. It must be at frozen, not I'm sorry, no, at material. Okay, and also the pillar diameter must be like this, like the volute. Okay, to avoid any overlapping the mesh. And so here add material, and here is add frozen to use sliding mesh technique. Now we have to make both our tangent. So I'm gonna use y plane, insert projection from this edge. Okay, and also this edge. I need both edges to avoid the problems. New sketch. If you use Ansys 15, this you must go to constraints and all the constraints you have to check both global and cursor. Okay, draw line, get this. Okay, here the distance, I need this distance, copy and paste this distance in the translate in -z. Okay, thank you very much. Now we have the impeller and volute, concentric, the same diameter, no problem. Okay, Okay, these things, please. Suppress. These are the dimensions. I don't need them. Okay. So here we go. So random design, gentlemen, you have to do. This is a very random design. I'm just showing you how to do the simulation. Now, if you have an outlet pipe and you want to add it to the system. For example, suppose that you have another pipe that you have to add to this system. The outlet pipe will contain the same flow material, for example air. So if you want to add it here, just you have to add an extrude to this, or make an extension like this. Suppose you have 100 millimeters outlet pipe or anything, you have to add it. Just apply it, add place material, because this is material, so add material. Direction vector is YZ. Yes, YZ, notice 100 millimeters. Okay, and so on. So now we have added the outlet pipe to the system. For example, suppose that I do not have this pipe right now, and it's a separate file. Suppose that you have, for example, okay, just suppose that you have a random pipe here. Okay, and you wanna add it to the system. Suppose it is not a box. Of course, you can do what I've just done here. Make an extrude. Also, after the extrude, if you have a V-shape pipe, what you have to do is go to XY plane, generate, sketch projection, this edge, generate a plane, sketch, I'm sorry, measure this distance, please. Okay, this is, I need the vertical. The vertical distance. Cancel. Line. Make it vertical. Okay, I need this. To go here. Cancel. Control Z. Align. Yes, it has to be this shape H. Now I have the dimensions. Carry out another plane. Okay. So this is the distance from here to here. Also, you can, if you have another, okay, now what if you have a V-shaped outlet pipe? Okay, what you have to do is this, here is YZ plane, yes, and this plane, generate a plane, and of course you have to know what is the outlet face of the outlet pipe, the distance, suppose it, okay, suppose it 500 millimeters. So go, and we have to create new sketch in it. But please make sketch projection to get this face. Okay. So suppose that you have a V-shaped rectangle like this. It's a random rectangle. Now you can make Loft tool. Select the edges. Okay, I know that, I'm sorry, there is a problem in the Loft. Delete this, I don't need it. Loft. Select this face and these edges. Okay, now after this you have to make the projection for this face to start from it. Okay, here we go. Create a new sketch. Make a rectangle. Okay, but suppose that the dimensions, okay, you cannot modify it. Delete it. from here to here. Let's know the dimensions to get the center point. There's a line. Okay, the dimensions. Okay, so this is the distance divided by 2. So we need to draw a line. The dimensions of this line. Here is our line. Okay, so H4 has to be 13.1869. Okay, so generate. This is the center. Also, I'll draw okay, and the dimensions V5 divided by 2. For 6A3. Okay, now I have the center point. So this is the center point, okay? Suppose that you have rectangular okay, from the center, dimensions from here to here, and dimensions from, no, I'm sorry. This to this, dimensions, okay, from this point to this point, okay, with L11, it's gonna be 12, and L9, gonna be 12. all this. 12 gonna be 24. It's gonna be 12, and here's 24. And here we go. Finally, gentlemen, this is the outlet pipe we have here. Of course, it's very long. I'm just showing you what you have to do. Okay. Notice that here we have a face, face. Select all faces. Just tools, merge faces. Okay. Generate. Okay. Now we have these faces are merged. Okay, also merge faces, we must do it for the impeller to avoid any problem with the sliding mesh. So select this body and hide all other bodies. This is the impeller with the new technique. Okay, no problems here if you wanna. Okay, no problems. And now we have to merge these faces for the sliding mesh, interfaces, tools, and merge, apply, generate. Okay, no problem now, no problem. Okay, so now we're gonna talk about the inlet pipe. You must have an inlet pipe, so just select also for this face and this face. Please merge them. Okay, here we go. Please select this edge, all these edges. Okay, and this edge, this edge, this edge. Also can merge these edges. Okay, skin loft. Edges must be equal number of edges. Okay, let's. Okay, think there is a problem or what? This is frozen. Okay, we have here a problem. No problem. Tools merge. Yes. Tools merge. Okay, if this does not work, okay, we're gonna use another trick to generate the other pipe. Okay, no problem. Okay, no problem. Okay, let's go to XY, create a new plane, this plane, projection, edge 2, generate, draw, sketch. Gonna make circle. Okay, here's our circle. And YZ plane, generate, projection, I need this edge, no distance, I'm sorry. Okay, this face, no plane, no sketch. Line from here to here, dimensions, okay, go and make sketch in XY from Z, Control V, then generate. Okay, I'm sorry, we have here, no, this plane, this sketch, I wanted sketch the projection of this edge, the edge of, yes, okay, to know line, dimensions, okay, XY, plane, generate, insert, this plane, here, this plane is offset Z, yes, this is what I want. Now, sketch, go, make the other circle. Also, sketch projection, project this, please. So here we go. Okay, and here we have two sketches, just Loft sketch 5. Sketch 6, sketch 13, and here is add material because this is at frozen. Okay, so add frozen, add material, and the volute is add material. Okay, now here we have this, and now we're gonna extrude this face, apply and add material. Okay, suppose it 50 millimeters. Okay. Okay, please hide this body. We have here two add material bodies, but we have two faces. Now you must merge these faces for sliding mesh. Okay. Now here we go. Okay, now show all bodies. So, ladies and gentlemen, finally we have this fan, and now, okay, here is the volute impeller at frozen, add material volute, and extrude add material, and here is add material. Okay, now close Ansys design modeler. Now let's open the meshing. The meshing is very important. Is a very important part for the complex geometries. Like I said many times, you can generate the unstructured mesh, but you have to carry out inflation around the blades to generate a structured grid. For the boundary layer or any other calculations that require structured grid. Or here unstructured grid, and now I'm going to show you how to make the inflation. And here the problem that you will face is the skewness. It must be not higher than 0.98, or the solver will face many problems for the conversions. Also, for the y plus calculation, you must know what is the first layer thickness or the first layer height. Okay, like I said in the centrifugal pump tutorial, we have here a model for the y plus calculation, but let's take a look. Okay, here to generate we want to generate this mesh, CFD, Fluent, sizing, fine, smoothing, fine, high, or make it low. You can check out all these things, just generate this mesh to see the skewness. Okay, the right statistics. Maximum 0.99, so this is not an acceptable size. Please make here minimum size, make it 5. Generate. Here is the calculations of y plus. You have to know your inlet velocity and Reynolds number. So the rho and velocity and the inlet, or the velocity, it may be in the inlet velocity or the impeller velocity or the blade terminal speed. Okay, this is the, it's not in the inlet velocity, this is the impeller speed. Here is the impeller terminal, the blade terminal speed. Speed, the rotational speed, omega multiplied by r as an approximation, 62 meter per second, and the first layer thickness, and y plus, you have to get the y plus, you have to determine it, and then you can calculate the first layer thickness. Here is delta, and here is meter. Okay, so you have to know what is going on, and to carry out these calculations. And the hydraulic diameter is the diameter of our impeller. Okay, suppose it 104. Okay, so let's see here, maximum 94. Okay, so this is good for the skewness, but you have to know what is the suitable for you. Okay, also you can add sizing for this, insert sizing, for the volute. Can make it 3 millimeters, and sizing for this. Notice that here, by chance, the impeller is structured grid, and this is very good. Okay, if your grid is unstructured, you can make inflation. But this, so the structured grid is not the default of all the models. Here is the skewness. Notice that the maximum now is 0.62. Wonderful. Okay, and also the grid is very good, and you can add sizing for the inlet pipe. Click on update. Okay, okay, very good. Wow, wonderful. Here notice that they are the same. Here is the interface, okay. Okay, now what I'm talking about is the first layer thickness. According to the calculation, suppose that your terminal velocity, that the rotational speed is omega, and the radius is r, and the terminal velocity is 62 or 50 meter per second, and the y required y plus 40 or 60, and rho is 1.2 as air. Also, the mu of the air, the dynamic viscosity of air three Kelvin, the dynamic viscosity 1.846. The density 1.17. And here is the radius, suppose it 140. Okay, no problem. And here is delta in meters, so the y plus or the first layer thickness is 0.48 millimeters. So here is the first layer. Let's check it out. I think it is 2 millimeters. So now we have to carry out some refinements. If this is unstructured grid, just you have to right click and select inflation. Okay, but this is a structured grid, so we're gonna use refinement. The refinement is for these edges. These faces, I'm sorry. Okay, apply, make it 3, and then update, and let's see. So if this is unstructured grid, select the same faces but using inflation. Insert inflation and select the same faces. Notice first of all you have to check out the maximum, okay, if it is less than 0.98. Now go here, okay, one side for refinement. Also can make a refinement and face mapped many things actually. Update. The structure grid is very useful for not being time consumer. Notice, notice here. So there are many ways. Okay, all of this is very good, but you have to reach 0.49 millimeters as a Y plus as a first layer thickness. Okay, very good. It's 0.5. Okay, it's okay, no problem. Now, so you have to carry out all the whole mesh for the impeller like this way. This is very good. And now we have the last thing is just we have to define for the 3D. It's okay not to define the interfaces, but I'm gonna show you how to define them. Also here is the inlet, and for this body inlet flow, and for this face interface 1 they will be detected automatically. Okay, now show all bodies, select the impeller, hide other all bodies, interface 2, interface 3 between the volute and the impeller, and this is the impeller flow. Okay, and show all bodies, select the volute, hide all other bodies, interface 4. Okay, volute flow, and the outlet. Okay, so here we go. Show all bodies. Now please close it. You will have to carry out the mesh. You have to complete it. Okay, just update the mesh to start Fluent setup. Okay, open starting Fluent. For answer theory guide, you can check out the turbulence models, and so here is the turbulence. This Ansys Fluent theory guide. All what you need is here. Okay, you can check out the sliding mesh and moving reference frame and many things here, and sliding mesh, using sliding mesh. Let's check out the sliding mesh here and the interface and the basic of it. Okay, and the turbulence, and also the setup of every models, k epsilon, and this very important. So here double precision is very important, and if you have Perl, you can check out the number of your processors here, the performance for threads. So you can here choose 4 threads, or so my maximum here is 4. If you have 8 or more, you can choose all of them. Okay, so for this we're gonna load it. A problem with the geometry and it's not the time to fix it right now, so I'm using another geometry. When you open Fluent, you will find it steady, so make it transient, and then the models, open it, choose k epsilon and anything you need here according to your knowledge, and you must study before choosing any of these models. Okay, you are a lot of here. This is the beauty of Fluent. You have here a lot of options, transition SST, and large eddy simulation. Okay, many things. Okay, standard LNG, realizable. You can please choose the recommendations, and here the material is gonna be air. Okay, you can add from Fluent database any material. Okay, and the cell zones will find impeller flow, inlet flow, and the impeller flow. When you open it, this what we say, you see. So click on mesh motion to make slime mesh. Okay, and then define the radian per second, the rotating speed, and the air. Here the material is air, must be air, and then the inlet flow, air, no other, volute, air. Okay, no mesh motion. The boundary conditions, the inlet and the outlet. So it's recommended to use the velocity inlet or the mass flow inlet, or whatever you want. The intensity and viscosity ratio, you can choose k epsilon and any other option here. Please, the turbulence intensity, you must get it from good references. and because it affects the solution. Okay, also the hydraulic diameter, maybe the impeller hydraulic diameter, the hydraulic diameter is the impeller. Also you may choose the viscosity ratio, but please you have to study before choosing this. Also the outlet is going to be the pressure outlet. Please set the gauge pressure, and the same options are here. Okay, so the mesh interfaces by default they are defined by default, so do not do anything here. No dynamic mesh. The reference values is very important to know it. You can run the simulation without dealing with it now, but if you wanna, for example, for the centrifugal pumps, if you wanna get the numerical efficiency, you have to get the reference area and all this data to know the force acting on the impeller. Then you can know the power input to the pump by the torque multiplied, moment multiplied by the rotation speed. Okay, here the reference zone is the impeller, and the solution methods here is the default is simple, but for our paper here they choose symbolic, and please you have to study why and why not. And here the gradients, please check out all of these things, you must be able to know. And the solution controls, you have the under relaxation factors, all of these things are in the Fluent 3 guide. Of course you can make monitors. Suppose that you want to make a monitor to study the pressure fluctuations, so you have to get x, y, and z, the coordinates, and then create this monitor. After this, go and create monitor. Choose the monitor that you created. Okay, let's make a monitor. Surface point, create point 18. So this is the point. Area weighted average for static pressure. Write a file. The axis flow time, iteration time step, and click OK. This will make you get this data, time and pressure, static pressure, and it will be fluctuations. Okay, after finishing the simulation. And the initialization, you have to initialize your simulation. Okay, here you must see the conversions, -7, -7, and -8. If the solution is divergence, it will tell you that the convergence does not achieved. Also for the monitors, you can increase the accuracy. The default here is 0.001. You can increase this accuracy for the convergence. And the calculation activities auto save every 1000 iterations or whatever you want. Also you can create animation files like this, make it pressure per time step, define the pressure contours, static pressure, failed to see the whole thing, and then you can click on display. Okay, and then you can run the calculation, the time step, check case if there is any problem. You'll get any the recommendations, a number of time steps, and here maximum iterations, and then you can calculate. Okay, so this is the setup of Fluent. Now after finishing the solution, I'm going to show you how to calculate the FFT. Okay, gentlemen, here the Matlab initializing. Please go to the folder. Okay, the desktop where I have the file. Here is the code load, the name of the folder. You will find automatically you will find your files motor surface motor 1 and 2 and 3, but here I got this, I copied it and renamed it mon1.out. Okay, then you have to load mon1.out and semicolon, and here is the time, the pressure, and you're in kilopascals, and this is the whole code for the FFT. Just copy it, and here the copy and paste. Okay, and here is the spectrum, also the FFT, and here is the spectrum pressure. So let's take a closer look on the spectrum. Okay, wonderful. Here is the FFT peaks, and here is the pressure fluctuations, and here is the amplitude, and here is the small amplitudes. Notice the small amplitudes are responsible for this, and the big amplitude are responsible for this FFT, high FFT as a peak. Okay, so this is the method, and of course you have to make monitors at the critical locations around the impeller and the volute tongue, and the locations that you have measurements. You must have measurements to validate it against the numerical results. The last thing, gentlemen, you can use BladeGen here. I'm going to show you last thing for this tutorial. Open BladeGen. You can new radial impeller like this, something like that, and close, transfer to new geometry, and then refresh the geometry to open it. Okay, yes, starting design modeler. Here we have the flow path, and the blade automatically so exported. Step file. So gentlemen, after exporting it, please import it directly from the file. Okay, no need to open any CAD geometry or any CAD process, just export it from the geometry here, export it, and please import it again here, and here is the blade, please suppress it. Okay, now we have the flow path. Create pattern, circular geometry, yes, axis, xy, copies, suppose that you have 4 copies, okay, or 5, 6, 8. I'm trying just because I do not know the real number of blades. 10, 13, 14, 15, 15 blades. We have here 15 blades. This is the real design. In 0 seconds or 0 time, you have the blades or the flow path of this design, okay? Like what we have just seen in BladeGen. If you open BladeGen, you will find the same design. Why I'm doing this? I'm doing this for the people who don't want to use CFX because they do not find large eddy simulation in CFX, so you can import, so you can carry out the process now, get your volute, and here is the flow path of your design from BladeGen or Vista. I think you can do it by Vista, I'm not sure. And then you can carry out the mesh in Ansys, and then you can open Fluent and carry out your simulation using large eddy simulation or any options that are not available in CFX. Okay, but here I think no need for this pattern. Why? Because you can take the benefit of the periodicity. Notice that in CFX you can solve the domain only using one passage or two passages. So after generating the mesh, you can name the selections of these faces, okay, as the periodic face number 1, and this is the second periodic phase is this exactly. Check out the CFX and you will know how to do this. So this is the periodic phase and the other is the periodic phase. So this is for the periodic interfaces. Okay, after this, so this is the geometry. You can make it here mesh. So in Fluent, after finishing this, you have to get the mesh interfaces. Okay, the content creations, but you can create the periodic. You can name this the interface as periodic, and you will find here the okay, just wait a minute. We'll find here already periodic 1 and periodic 2. So you can select periodic 1 and here periodic 2, and please make this periodic boundary conditions, and they are rotational and auto compute offset, or you can make it the angle. The angle here is suppose that you have 15 blades, so divide 360 by 15, so it's gonna be 24 for this case, okay? And that's it, and then you can create. Okay, gentlemen, thank you very much. I think that I showed you many things today. Also here the FFT Fourier transform for this doctor, and the signals you can get this from the internet, and YouTube has many many videos about fast Fourier transform and the code. You can get it, and you can see videos about fast Fourier transform. Thank you very much. I hope I hope this helped you. Wassalamu alaikum wa rahmatullahi wa barakatuh.